guys, it's Miss Treese. Today in this video, I'm going to talk about a little more about solids, liquids, and gases, but specifically we're going to focus on heating curves and the calculations that go along with those. So you're definitely going to want a calculator, and you may want a periodic table as well. Okay, let's get started. So a heating curve is basically a plot of temperature. Over here on our y, ooh, that's not a highlighter. Okay, of temperature, that's over on our y-axis versus time. And guys, on our time axis, basically energy is being added at a constant rate. So time, think of like as your time is increasing, that also it's the amount of energy or the heat being put in it as is increasing as well. So energy is being added, or like your heat is increasing. Now, guys, as our energy is added, what's going to be happening here is we're going to see two types of changes, either just the change in your kinetic energy or the change in your phase. All right, we can kind of see that in our graph in that we have these like slanted sections and we have these flat sections. So they represent different things. So let's go ahead and talk through them. So first off, right here on section A to B, this is where we have our solid phase. All right, and all that's happening in our solid phase is if I'm moving from A to B, is that I am changing my kinetic energy. So if you guys remember, I think we talked about this a few days ago, but temperature is directly related to kinetic energy. So as your temperature increases, your kinetic energy is going to increase. As your temperature decreases, your kinetic energy is going to decrease. So they are directly related. So right here, we have a change in our kinetic energy. That's what's going on. Then next we have B to C. In B to C, you guys can see that we kind of level out and our temperature is no longer changing. That's because it is a phase change. So all of the energy is still being added, but instead of the energy going to heating up our substance, instead it's now going to breaking those intermolecular forces. So we have a change in potential energy here. So that one would represent melting or freezing. So you're either going from a solid to a liquid or from a liquid to a solid. So melting or freezing. And what we kind of use to calculate here is our heat of fusion. And our heat of fusion is just the amount of energy that it takes to be put in order for our solid to melt or for our liquid to freeze. It's just the opposite sign if we're talking about liquid to freeze. So we would use our heat of fusion there to help us calculate that. This represents on this line, this B to C represents our normal melting point, which is our melting point at 1 atmosphere of total pressure. And things melt when they have the same pressure at 1 atmosphere. So yeah, that's what's going on there is we're melting. All right, and then next we have line C to D right here. And once again, that represents our liquid phase. So that is our liquid phase, and it's our liquid being heated. So once again, we have a change in kinetic energy here. As it heats up, our particles move faster and faster, so they have more kinetic energy. And then D to E. I'm trying to pick pretty colors, guys. All right, D to E right there. We have our boiling / condensing. And again, guys, all of that energy that's being put into our graph right there is going into breaking the intermolecular forces versus heating it up. So that's why we don't see a temperature change here. So it is changing our, writing is so hard, guys. It's changing our potential energy here. And then finally, our last little piece on the graph is, just do this dark color right there, E to F, and that represents our gas phase. So that is the heating of our gas. So once again, we are changing, oops, man guys, I'm having all the problems today. We are changing our kinetic energy here. As our temperature goes up, your kinetic energy will continue to increase. So that's kind of, again, it's a journey of our phase diagram. So we started a solid with our particles really close together. As it heats up, those particles move faster and faster till they're able to overcome those intermolecular forces of attraction between them. And when that happens, they start to turn into liquids. And so on that line from B to C right there, we would have kind of a solid liquid mix. It's like an ice cube melting. You still have the cube and some water. So that's what's going on there. So we have that, and it's starting to break, kind of starting to form a liquid. And then when it completely melts, we've just got a liquid. It's going to heat up. As it gets hotter and hotter, it's going to move faster and faster till it can overcome those intermolecular forces of attraction. And then it becomes a gas. So there you go. That's what's going on there. So now let's talk about the different phase changes and energy required for them to happen. So we're going to start by talking about phase change. And during our phase changes, all the energy is still being added during those phase changes. Like it's being added at a constant state throughout our heating curve. But all the energy is going to changing the phase and breaking those intermolecular forces. So our temperature remains constant. So where we are going to use this equation is when we are just looking at the phase change. And so like on our graph, it's going to look like the flat line areas are where you'll use this equation. And the equation is that our phase change, our amount of energy that goes into our phase change, is equal to amount of substance times our heat of either fusion or vaporization. Now, guys, sometimes it's in moles. Other times it's in grams. So you really have to pay attention to the units on your heat of fusion or heat of vaporization to see if it's in moles or grams there. So definitely pay attention because it's about 50-50. Sometimes it's in moles, sometimes it's in grams. If it is in moles and you're given amount of substance in grams, then you need to make sure that you convert. All right? Okay. So heat of fusion or melting is the energy basically required to melt 1 gram. All right. It is an endothermic process. So guys, remember endothermic, you have to put energy into it for it to happen. So it's going to be positive. So since we have to add energy to go from a solid to a liquid, you're going to have to put energy into it. So it's going to be a positive value for that one. Now then, if I'm going from a liquid back down to a solid, that is actually going to release energy because I'm going from, I always think of it about the movement. So liquids, their particles move a lot more than solids do. So obviously it's going to take energy out because they're not going to have to move as much. So it's not as much energy required. So if you're talking about going from solid to liquid, it's going to be a positive value. But if you're going from liquid to solid, you're going to flip that sign and it's going to be a negative value. So heat of fusion is for melting and for freezing. You just flip the sign. And then same thing with heat of vaporization. So if you're going from a gas or a liquid to a gas, all right, liquids don't move very much. Gases move a lot. So we have to put that energy in. So that's going to be an endothermic. So our heat of vaporization will be positive. But if I'm going from a gas to a liquid, it's going to release energy. So it's going to be exothermic. So it's going to be negative. Hopefully that makes sense. But basically, to sum that up, if you have a positive change in energy, it's absorbed, while a negative means energy is released. Yay. Okay, so now let's do a couple practice problems using our equation up here. Q is equal to amount of substance times our heat of vaporization, or just your heat, I guess. It's either going to be fusion or vaporization. So pay attention to what your problem is asking. All right. So this one says, calculate the amount of heat required to condense 5 milligrams of steam at 100 degrees Celsius to water at 100 degrees Celsius. So there's no temperature change here. You guys will see that it is important to note that there is no temperature change. We are only paying attention to how much energy it takes to change our enthalpy here. All right, and we're going to use our values just from up here. So we are condensing steam. So that means we are going from a gas to a liquid. And our heat of vaporization is 2,264 joules per gram. All right, so first thing is my equation is Q is equal to mass, because my heat of vaporization that I'm using from the previous page is in grams, joules per gram, times the heat of, and here we're going to use the heat of vaporization. Okay, so first thing I noticed is that this is in milligrams. It's not in grams. So I need to convert from milligrams to grams. All right, so you guys can move the decimal if you want to, but I'm going to show you guys how to do it this way using some dimensional analysis. So milligrams on top, need to drop it low and put it on the bottom. And I know that there are 1,000 milligrams in 1 gram. So then 5,000 divided by 1,000 times 1 gives me 5.0000. I do have to keep all those zeros because of sig figs. I know, everybody's favorite. All right, so now I'm going to plug it in. So Q is equal to 5.0000 grams times our heat of vaporization. Now guys, here we are condensing. We are going from a gas to a liquid. So it's going to release energy because it's an exothermic process. So instead of having a positive value here, I'm going to have a negative value for my heat of vaporization because I'm going from a gas to a liquid. So negative 2,264 joules per gram. All right. So we can see that our units are, sorry, I'm going to move my picture for a second, are going to cancel since I have grams on the top here and on the bottom over there. I'm going to be just left with joules. All right. So I'm going to plug it into my calculator, 5.0000, I think, times negative 2,264. All right, plug it on in, and I already did this. Let me find it. So when I plugged it in, I got negative 11,320 joules. I need to have 5 sig figs because my mass has 5 sig figs. So I just need to add a decimal at the end. So negative 11,320 joules of energy is required or is going to be released actually whenever we condense that gas to water. All right. All right. So why don't you guys go ahead and do number 2 on your own. I just want to caution you right here that this is in kilojoules or your heat of vaporization is in joules. All right, so you guys go ahead and try this one out, pause the video and try to do it on your own. And then whenever you're ready, restart and we'll go over the answer. Okay, so first thing I did on this problem is I converted my energy from kilojoules to joules since my heat of vaporization is in joules per gram. All right, and then it is absorbing energy because it does say it's going through vaporization, so that is an endothermic process where it's taking energy in. I know that my equation is going to be mass times my heat there, and so I'm looking for mass in this one because I've been given the energy and given my heat of vaporization. So I manipulated my equation and said mass is equal to Q divided by H. So then I have my energy, which would be 5.00 times 10 to the 5th joules divided by 21.0 joules per gram. And so I get left, after I solved that, I was left with 2.38 times 10 to the 4th grams. All right, guys, there you go. All right, so this one says the heat of fusion for different substances are listed below. If samples of equal mass were heated on the same source, which substance would completely melt first, and then which one would take the longest and why? Okay, so you can see we have 3 different heats here, 181 joules per gram, 321 joules per gram, and 91 joules per gram. All right, so the less energy it requires, the faster it's going to melt. So the one that's going to melt first would be substance Z, just because it doesn't require as much energy to melt, so it's not going to take as long for that process to happen. It's not going to take as long to get that much energy put into it. And then which one's going to take the longest? Well, that's going to be substance Y, because it's got the highest heat of fusion. I guess that one's fusion. Yeah, highest heat of fusion. So it's going to take the longest. Okay, so now we're going to talk about if we have a change in temperature calculation and what that looks like. So guys, so far what we are going to talk about now is only if we stay in the same phase. All right, and if we have a change in temperature, obviously that MH doesn't work any longer because it's just joules per gram. All right, but we have a change in temperature there. So we have to use our equation Q equals MC delta T. Hopefully you guys remember this one from last year, MCAT. So M stands for mass, C stands for specific heat. And it's the amount of energy it takes to raise 1 gram of a substance by 1 degree Celsius. And then finally, delta T is change in temperature. So delta T is equal to your final temperature minus your initial temperature. If you have a really low specific heat capacity, it means it doesn't take much energy, so it's going to heat/cool very quickly. And we call those conductors. And then if you have a really high specific heat capacity, it takes a lot of energy, so it's going to heat or cool slowly. And those are called insulators. The specific heat for water is 4.184 joules per gram degree Celsius. Now then, that is liquid water, and water does have a different specific heat when it is a solid and when it is a gas. All right. So for our first question, it says, calculate the heat required to warm 750.0 centigrams of water from 10 degrees Celsius to 80 degrees Celsius. All right, so we're going to use our Q equals MC delta T. First thing, though, is we are in centigrams of water. Our specific heat of water is just in grams, so we do need to convert that. So I have 750.0 centigrams of water. Oops, centigrams on bottom, and I know that there are 100 centigrams in 1 gram. So that tells me that I have 7.500 grams of water that I'm working with. All right, so now we're just going to plug everything in. So Q is equal to our mass, which is 7.500 times our specific heat of water, 4.184 joules per gram degree Celsius. I forgot to put my units on my mass. Whoops. Times our change in temperature. So I'm going to go final minus initial. So my final is 80.0 degrees Celsius minus my initial, which is 10.0 degrees Celsius. So that change there would then be 70 degrees Celsius. So then I can just plug everything into my calculator and get an answer. So I'm going to go ahead and change this since I did actually solve it. 80 minus 10 degrees Celsius would give us the actual answer of 70 degrees Celsius. Okay, so after you've plugged it in, I got pretty big number. My temperature has 3 sig figs. That's my fewest number. So my answer should have 3 sig figs. So I got 2.20 times 10 to the third joules as my answer. So it takes that much energy to heat water from 10 degrees Celsius to 80 degrees. All right, now then let's do this one. So this one says determine the specific heat capacity of an unknown if 20.4 joules of heat are absorbed in lowering the temperature of 10 degrees of an unknown substance from 42 degrees Celsius to 35 degrees Celsius. Okay, so this time I have Q equals MC delta T, but I'm trying to solve for C. So that means C is equal to our heat divided by M delta T. All right, so let's go ahead and plug everything in. So C is equal to 20.4 joules divided by our mass, which is going to be 10 grams, times divided by our change in temperature. So our change is going to be 35.0 minus 42.0, which is negative 7.0 degrees Celsius. So we've got a negative there. So then we're going to go ahead and plug that in. Okay, and when I do that, I got negative 0.29 joules per gram degree Celsius. It should be 2 sig figs because our temperature only has 2 sig figs after we do our subtraction there. Okay, but this is our last part of our video, and in this part we are just going to just do our very end thing where we are going to kind of put all of this together. So put together the Q equals MC delta T and Q equals MH. All right. So let's start with our problem. So our problem says how many joules, so how much energy, we're looking for Q here, are needed to convert 5 grams of ice, so there's our mass, at negative 15 degrees Celsius to steam at 130 degrees Celsius. So guys, what we can see here is we're starting with a solid, all right? Then we're going to become a liquid, and then finally we're going to end up at a gas. So we are going through 2 phase changes, and we are going to be in all 3 states of matter. So that means that we need to, we need to do a variety of different equations here, all right? So if I look at my graph, I'm going to kind of label things on my graph now. So I'm going to come down here, all right? I know I'm starting at negative 15 all the way at the bottom, all right? And then I know that it's water, so that means that it's going to melt at 0. And then once it's melted, it will boil at 100. And then from 100, we end at 130. All right, so I have kind of all 5 sections on my graph here. All right, so now let's kind of talk about what's going on. So let's talk about this first one, our solid section. Our temperature is changing, so for that one, we have to use our MCAT equation because our temperature is changing. Then right here, we're undergoing melting, so we're going to use our phase change equation, Q equals M times H. Then we have liquid right here, where we once again are undergoing a change in temperature. So Q equals MC delta T, I guess I should say. It's change in temperature, so Q equals MC delta T. Then we have our phase change, so Q equals MH. And finally, last but certainly not least up top here, we have one more Q equals MC delta T, where we're changing temperature. All right, so let's get to it. So we're going to start with our first little segment. So segment 1, all right? And it's a change in temperature here, so we're going to use the equation Q equals MC delta T. All right, so our mass is 5.0 grams times our specific heat. So we're in ice at negative 15 degrees Celsius. So our specific heat is going to be 2.10 joules per gram degree Celsius times our change in temperature. So final minus initial. So our final temperature here where we melt will be 0. So 0 minus negative 15 gives us a temperature change of 15 degrees Celsius. All right, so I'm going to plug that on into my calculator. And guys, sig figs are important here, so check through. Remember when you're multiplying that you always use the fewest number of sig figs. So for us, our 5.0 has 2 sig figs, so our answer should have 2 sig figs. So I got 160 joules. All right. Now, guys, I'm just going to go ahead and tell you this problem at the end, it's going to be a little easier to do our sig figs with kilojoules. And some of our answers are going to end up in kilojoules. So I'm going to go ahead and convert to kilojoules for right now. So when I do that, I basically just divide by 1,000 to get my kilojoules from my joules, and I get 1.6 kilojoules for segment number 1. All right. Now for segment number 2, I am melting. All right, and so I'm going to use this equation right here, my Q equals M times H. Now, guys, what I want you to notice about our H is that our H is in units of kilojoules per mole. So I'm going to have to convert from grams of my substance, because I have 5 grams of my substance, to moles before I am able to use that, my Q equals M times H. I'm going to actually show you guys that you can actually just do the dimensional analysis here instead of having to like plug it into the equation. So I have 5.0 grams of water. I have to convert it to moles. So drop your water low. And I know that I have 18.018 grams of water in 1 mole of water. Now guys, notice, if you notice, our heat of fusion is in kilojoules per mole. So we can actually just plug our heat of fusion in here. So then from our heat of fusion, I know that in 1 mole of water, it is 6.01 kilojoules. That just kind of saves us a step of having to like find moles and then solve for it. You can just plug it all into the same equation, save yourself a little time by plugging it into the dimensional analysis. All right, so then I would have 5 times 6.01 divided by 18.018. And I got, when I did that, I got 2 sig figs once again, because our 5.0 only has 2 sig figs. I got 1.7 kilojoules for that one. Okay, so now we're moving on to our third segment on our graph, which is where we are a liquid. So once again, I am going to be using my equation, Q equals mc delta T. So our mass is 5.0 grams times our specific heat for liquid water is 4.184 joules per gram degree Celsius times our delta T. So in this one, we're not given either either end point temperature, but I know that my water boils at 100. So my final temperature will be 100 minus my initial temperature, which should be 0. So 100 minus, or 0, final minus initial. So 100 minus 0 gives me 100 as my delta T. All right, plug it on into our equation. So 5.0 times 4.184 times 100 gives me 2 sig figs once again. So 2,100 joules with those 2 sig figs. Like I said on this one, it's a little easier to solve the end number in kilojoules just to do your sig figs. It's a little easier. So 2.1 kilojoules here. All right, next, what color did I use? I forgot. Pink. Segment number 4. Once again, we have a phase change. So once again, our phase change information is given to us in kilojoules per mole. So we have to convert that grams to moles. And then just like the last time, I can just plug it all in like a little dimensional analysis problem. So I have 5 grams of water. I know that the molar mass of water is 18.01, and I think I actually messed up, and it should be 18.016 grams of water. Shouldn't change my answer up here, but I don't know where I got 18.018. I don't know, guys. Sometimes I just lose it for a second. Shouldn't change your answer at all, but that is the actual molar mass of water. All right, is 1 mole of water. And then from our table that we have, 1 mole of water is going to require 40.07 kilojoules. So then once again, I have 2 sig figs and I solve it. So 5 times 40.7 divided by 18.016 gives me, what is that? 11 kilojoules. And our last, but certainly not least segment right here is once again a change in temperature. So Q equals mc delta T. And I have my mass of 5 grams of water times my specific heat of solid water, which I think is 2.0. Yeah, 2.0 joules per gram degree Celsius times my change in temperature, which we're starting at 100 and we're ending at 130. So 130 minus 100 gives me 30 degrees Celsius here. So I have 5 times 2 times 30. 2 sig figs on my, sorry guys. Yeah. 2 sig figs on my answer once again. Actually, this one only has 1 sig fig because your change in temperature would only have 1 sig fig. So we get 0.3 kilojoules. All right. Now I'm sorry, 300 joules. I keep skipping ahead, guys. 300 joules, which is 0.3 kilojoules. All right. Now what I'm going to do is I'm going to take all those numbers that I got and I am going to add them together to give me my total number. So I have 0.16 plus 1.7 plus 2.1 plus 11 plus 0.3. All right, and when I plug all of those into my calculator, I got 15.26 kilojoules. Now, guys, your rules for adding and subtracting with sig figs are that you always keep the fewest number of decimal places. So our 11 has 0 decimal places, so that means we're going to round to 0 decimal places, which would be 15 kilojoules. And like I said, adding the kilojoules was just a little easier than the joules. So to get your answer in joules, you'll multiply times 1,000, and that leaves you with your final answer being that it requires 15,000 joules in order to heat 5 grams of water from negative 15 all the way to 130 degrees Celsius. And there you go. That is our heating curve. So hopefully that made sense. If you have questions, email Mr. Oglesby or myself, and we will be happy to help you. All right, guys. Bye.